These are the notes for AP Calculus on the topic of the first fundamental theorem of calculus. So, unlike derivatives, where we have a specific notation for the derivative in function notation, if this is your original function, the derivative is written as f prime of x. For antiderivatives, there's not a specific notation. So oftentimes what they'll use is a capital letter to represent an antiderivative, but it always has to be defined as that. It doesn't automatically mean the antiderivative. So it says capital F of x is an antiderivative of lowercase f of x. And if f of x is continuous on some interval from a to b, then the definite integral from a to b of that function is defined to be this. So the way that's written, when you find the antiderivative, we just defined it to be capital F of x. So you have capital F of x. And then the official notation, the way it's written, is you write a vertical line right after that and transfer what these are called are the lower and upper limits. Actually, let's define some terms first. This whole thing is referred to as the definite integral. And the way you can tell it apart from an indefinite integral is it has, usually these are specific numbers, these are constants a and b here, that are referred to as a is the lower limit of the definite integral, and b is the upper limit. And they come from the interval you're looking at, in this case, from a to b. So when you find the antiderivative of lowercase f of x, which we define to be capital F of x, then the way it's written, after you do that, is you put a vertical line and then you put the lower limit over here, a, and the upper limit over here. And then what you do, you can see right here, is you substitute in the upper limit first, in for x, and then always subtract what you get when you substitute in the lower limit for x. So let's see how this works on some specific problems here. And there's lots of different applications for this definite integral, and we're just going to see one of those in today's lesson. So one of those is determining the area between the curve and the x-axis. So up until this point in your different math classes, you most likely only learned how to find the area of geometric shapes, triangles, rectangles, squares, trapezoids, circles, etc. However, that's limiting because not everything is a geometric shape. But with calculus, we can really find the area of anything as long as we have the function for that. So in this case, what we have is we've got the graph of y equals 9 minus x squared. You can see this parabola here. So if we want to find the exact area on the interval from -3 to 3, that's like our a and b here. In this case, it happens to be the x-intercepts, -3 and 3. Then we can use the definite integral to get what that exact area is. So to find that area, it would equal the definite integral from a to b, in this case, -3 to 3. The lower limit goes right there, the upper limit goes right there. And then we integrate whatever we're finding the definite integral. In this case, 9 minus x squared is our function, and then, of course, times dx. But previously we've looked at this differential, this infinitely small change in x represented by dx, as just primarily indicating the variable that we were using when we were integrating. But it has more meaning to that when you look at a definite integral. So let's go ahead and draw in here. You can really draw it anywhere in this region here, but usually it's easiest to work with when we get to more advanced problems if you draw it in the first quadrant, if possible. So we're going to draw an infinitely thin rectangle, or try to draw an infinitely thin rectangle. If we can't draw it infinitely thin, you wouldn't be able to see it. So we just draw a really narrow, thin rectangle here. Like that. And the width of that rectangle is what dx represents in a definite integral. Which makes sense if you think about it, because the number delta x is any change in x, And dx is a very similar concept, except that it's an infinitely small change in x. So that creates an infinitely thin rectangle here. So the reason why this works, to find the exact area, what's happening here, this dx here, that gives you the width of this rectangle. And notice the height of the rectangle is based on where the function is. In other words, what the y-coordinate is, where that rectangle is. So that's y is represented by 9 minus x squared. So that part gives you the height. So you can see this would give you the area. That's just the 9 minus x squared times dx. That would give you the area of one of those infinitely thin rectangles. But the way this works with calculus, we're integrating all of those rectangles starting at -3, stopping at 3. So starting with the infinitely thin rectangles here and adding up all those, or integrating all of them, all the way up until our upper limit 3. And that's how it's able to calculate the exact area under the curve, between the curve and the x-axis here. So on this one, when you integrate 9, remember they're separated by mass, so we can integrate each one separately. There's not really a function inside here, so this doesn't require u substitution. So you get 9x, and when it's a constant you just multiply it by the variable, because the derivative of 9x would be 9. And then using the power rule for integration on the x squared, that would give you x cubed over 3. Evaluated from -3 to 3. That's the official notation. Now notice one thing we didn't put here that we always put on the indefinite integrals is that plus c. It's not wrong if you put it there, but I'll show you in just a little bit why it's not necessary to put it there on a definite integral. Okay, now that's the official notation. However, I found it's useful to actually modify this slightly just for practical sake, especially when sometimes we'll have constants on the outside of these definite integrals. Instead of just writing a line there, I've just turned it into a bracket. Now that's not the official notation, but the reason why I like it, it shows you this whole thing, 9 minus x cubed over 3, that whole thing we're going to be substituting in the 3 and the -3, not just the x cubed over 3, which if with the line it might look like it's just that part. And when we have constants on the outside, it gives us a place to put those constants here. So not official notation, but just for practical sake, it tends to come in handy, I think. Okay, so now remember what the first fundamental theorem of calculus says. We first substitute in the upper limit. Always start with the upper limit first. So we're going to substitute that in and then subtract what we get when we substitute in the lower limit. So let's substitute in the upper limit, positive 3. And when we do that, we'll get 9 times 3 minus, substitute 3 in there for x, so 3 cubed over 3. And then subtract, and then I'm going to put this in parentheses, because we're subtracting this whole thing, what we get when we substitute in the lower limit of -3. So that would be 9 times -3 minus -3 cubed over 3. Now, before we simplify this to figure out our answer, let me pause and explain why I didn't put that unknown constant plus c that we always need for an indefinite integral. Well, there still could be an unknown constant when you integrate this, because any constant has a derivative of 0, so it could be anything. But let's see what would happen if we put that plus c in here. So you don't have to write this in, just kind of look and see. So if there was a plus c there, well, then when we plug in the 3, we'd have a plus c here. And then when we substitute in the lower limit of -3, we'd have a plus c here as well. So do you see what would happen with those constants? You'd have a plus c here, and this negative would distribute it and make this a negative c. And see how this would cancel out? So that's why on the definite integrals you don't have to put the plus c, because every single time they're always going to cancel out anyway. So there's no need to have them there. Unlike the indefinite integrals when you do need that unknown constant. Okay, so let's finish simplifying this now. So 9 times 3 is 27, minus 3 cubed is 27 divided by 3 gives you 9. Then minus 9 times -3, -27. -3 cubed is -27 divided by 3 is -9, but this negative out in front makes it a positive 9. So that 27 minus 9 gives you 18, minus -27 minus 9 is -18. So it's 18 plus 18 gives you 36. And we're talking about area here. So the area of the region enclosed under this curve, between the curve and the x-axis, from negative 3 to 3, is exactly 36 units squared, since we're talking about area. Now, it's not always going to work out to be a nice, perfect integer like this, 36, and we can get fractional answers. That can happen. If you want to see if this answer seems reasonable, well, just think about, what if this was a triangle right here? Well, if we had a triangle right here that kind of follows the shape, it'd be 1/2 the base times the height. The base would be 6. The height would be 9. So that would give you 54 times 1/2 is 27. So you can see, though, that triangle area would be smaller than this. So 36 units squared does seem reasonable. It is bigger than the 27 we would get if it was just a triangle. All right. Let's take a look at one more. This one, we've got the graph of y equals negative square root of x. And interval, in this case, from a to b is from 0 to 4. So 0 is an x-intercept right here. But notice 4 is not. These don't have to be x-intercepts for you to give you the area. If it's not an x-intercept, then what you can do is just draw a vertical line right here at 4, the upper limit. So what we're finding is the area between the curve and the x-axis right in here, in this region. So again, we can draw a representative rectangle in there that represents the infinitely thin rectangles that we're adding up to get the area between the curve and the x-axis. And again, that width is represented by dx. So let's set up the integral this time. To find the area would be the integral from a to b, in this case 0 to 4. This time our function is negative square root of x, and then times the width dx. So to make this easier to integrate, remember constants can be pulled outside the integral, so I'll pull that negative on the outside of the integral. The square root of x, to make it easier to integrate, to find the antiderivative, will be easier if we write it as x to the 1/2 in rational exponent form. And then when you integrate x to the 1/2 using the power rule, that would give you x to the 3/2. You add 1 to the exponent. Divided by 3/2, but that's the same as multiplying by the reciprocal, 2/3. And then again, this is the official notation, 0 to 4. But then I modified it just slightly to make it a little more user-friendly. Turn it into brackets that way. There's a nice place to put the negative on the outside. And notice after you integrate, sometimes there's other constants you can pull out to make your calculations a little simpler and less likely to make a careless mistake. So notice now we've got a 2/3. You could pull that on the outside as well, along with a negative. So we've got negative 2/3 on the outside. And then what's left is x to the 3/2. But that'll be easier to substitute in our lower and upper limits if we write it in radical form. So if you switch that back in radical form, that would be the square root of x cubed, evaluated from 0 to 4. So then we have negative 2/3. Then you can substitute in the upper limit of 4. So that would be the square root of 4 cubed. And then always subtract what you get when you substitute in the lower limit of 0. So that's square root of 0 cubed. So you have negative 2/3. And then the square root of 4 is 2 to the 3rd power is 8. Square root of 0 is 0 to the 3rd power is 0. So you have 8 times negative 2/3, which gives you negative 16/3. So you might wonder, well, we're talking about area, weren't we? How come we got a negative answer? Can area be negative? That doesn't make sense. So why do you think we got a negative answer? Well, if you look back at our region here, notice this region's below the x-axis. So all the heights are actually negative y values. So what that shows you is any regions below the x-axis, 16 over 3 is the correct area. But if you want the area, it's actually positive 16 over 3 units squared. But the definite integral gives you a negative answer when you work it out for any regions below the x-axis, as opposed to the previous problem we did notice was a region above the x-axis, so we got a positive answer. So keep that in mind. That'll come in handy, that knowledge, a little bit later on in the lesson. Okay, now let's just work on evaluating these definite integrals. Remember, we'll see later on some more applications besides just area. So this is just getting some practice working these out, as they'll have other meanings besides area. So we're not going to graph these to see what they look like. All right, so on this one, 4 cube root of x minus 2, notice again they're just separated by the minus. There's no functions inside, so it doesn't require u substitution. So the constant just stays there when we integrate. And remember, x cube root of x is the same as x to the 1/3. So when you integrate that, that'll become x to the 4/3. Divided by 4/3 is the same as multiplying by 3/4. And then minus, when you integrate 2, it's just a constant. It just, the antiderivative, it just gets multiplied by the variable, which is x. And again, here's our official notation from 1 to 8. And again, I'm just going to slightly modify that to make it brackets there. Then you can see we can simplify that. The 4's reduce out. In this case, there's not really a simple constant you can pull out on the outside, so you don't always have one you can pull on the outside. I'm just going to switch this back into radical form from rational exponent form to make it easier to evaluate. So that's the cube root of x to the 4th is the same as x to the 4/3. And then minus 2x. Okay. And then we can substitute, remember our upper limit first, so substitute 8, so it'd be 3 times the cube root of 8 to the 4th power minus 2 times 8. And again, remember when there's more than one term here, when we subtract, before we put in the 1, put a parentheses there to remind yourself you're subtracting the whole thing, not just the first term when we substitute in 1. So when we substitute in 1, we get 3 times the cube root of 1 to the 4th minus 2 times 1. And let's just keep simplifying this. So the cube root of 8 is 2 to the 4th power is 16. 16 times 3 is 48. Negative 2 times 8, negative 16. Minus, cube root of 1 is 1, 1 to the 4th is 1, 1 times 3, 3, and negative 2 times 1, negative 2. So I've got 48 minus 16, which is 32, minus 3 minus 2 is 1, so we get 31 is the value of this definite integral. All right, let's take a look at the next one here. So on this one, we're integrating 2 sine of x. So the first thing we could do to make it a little simpler is we can pull that constant of 2 out in front. So then it's just an integral from 0 to pi over 3 of sine of x dx. All right, so when you integrate sine, that gives you negative cosine. But rather than putting the negative here, it's actually easier, as we go from 0 to pi over 3, to pull that negative out in front along with the 2, because the negative is like a negative 1. It's a constant we can pull on the outside. That way, when you substitute in your upper and lower limits, you're not having to deal with that extra negative in there, which can make it easier to make a careless mistake. And remember, the way you remember if it's positive or negative on these trig functions is when you're finding the antiderivative or integrating, if your answer starts with the letter c, it's negative. If the answer does not start with c, then it's a positive antiderivative. So here it did start with c. All right, so this time we have a negative 2 out in front. And then we're going to substitute in the upper limit first, so that becomes the cosine of pi over 3. And then minus, we're going to substitute in the lower limit of 0, so cosine of 0. So negative 2, and then the cosine of pi over 3. Draw that real quick over here. Pi over 3 is in the first quadrant. Looks roughly like that. Same as 60 degrees. Cosine is the adjacent over the hypotenuse. So the adjacent here is 1, hypotenuse is 2, so that's 1/2. minus the cosine of 0. Well, 0 is right here. And remember, cosine is the x-coordinate, which is 1. So we have negative 2. 1/2 minus 1 is just negative 1/2. It's like 1/2 minus 2/2. And negative 1/2 times 2, the negatives reduce as well as the 2, so all that's left is just 1. Finally, let's take a look at some properties of the definite integral. So what you've been noticing probably is that when we set these up, we put the lower numbers our lower limit and the larger numbers our upper limit. But sometimes, for one or various reasons, they might be in with kind of the wrong order or the non-standard order. So if that's the case, what you can do to put them in the correct or more standard order is flip it and just remember you have to change the sign, make it the opposite sign. And if you think about why that would make sense, if we look back at our formula here, well, if we substitute these in, normally we do the upper limit minus the lower limit. But if it's flipped around, you see how that would just make it the opposite sign? For instance, if the first one we plug in we get 5, and the second we plug in we get 3, would give you 2. If you put those in the opposite order, 3 minus 5 would give you negative 2. Right? So that's why if you do have to flip them, all you have to do is change the sign. That's it. All right. The next definite integral property is if the lower and upper limits are the same, well, then the definite integral is going to be 0. A couple ways you can think about that. Well, if you substitute in the same number and subtract it, if let's say you get 7 minus and you plug in the same number, you get 7 again, you can see you'd always get 0. Or if you think about it in terms of the area between the curve and the x-axis, how much area is going to be enclosed if it's between, let's say, 5 and 5? Well, nothing, right? Because there's no area, it's not an interval if the starting and stopping numbers are the same. So either way, that's going to give you 0, whichever way you think about it. And the final property that will come in handy, it's easiest to see why this works if you draw yourself a little number line here. So let's say we have an interval from A to B. This is our big interval. We've got the definite integral from A to B. What this property is saying is, let's say we have some C value. What we can do to evaluate A to B is if we know the integral from A to C, notice that would give you this integral, plus the integral from C to B, would be this one. Add those together will give you the integral from A to B. So it's just saying basically taking the smaller intervals, add those up to get the larger interval, will work. Now usually the way we use this is when C is between A and B. But this property actually works even if it's not. We don't usually need it for that, but it works no matter what that constant is, regardless of whether or not it's in the interval. Okay, so let's take a look at a problem that uses those properties here. So this one says if the definite integral from -2 to 3 is of f of x dx is 11, we're given some other definite integrals and evaluate the following. So I think the easiest way to organize all this information is just on the number line. So let's go ahead and draw our number line there and organize it all before we start even answering these questions here. So we've got -2 to 3. If we look at all these, notice -2 is the smallest of all the numbers we're given, so I'll put that at the very end of our number line, the far left. But 3 is not the largest, we can see 9 is, so I'll just put 3 about right here. And this says the definite integral from -2 to 3 is positive 11. Since it's positive, I'm just going to assume it's all above the x-axis, even though there might be some above, some below with a net of 11. It's simpler to organize your number line if you just assume it's all above. So I'm going to put it above the number line with a little brace there and put 11. And then we're told from 4 to 3 of f of x dx is 5, that definite integral. But notice, this is one where these are not in a standard order, right? The lower limit it would typically be 3, the upper limit would typically be 4. So if you just flip it around over here, that would mean if we integrated from 3 to 4 rather than 4 to 3, the way you usually would think about it, well, remember our property here. when you flip the upper and lower limits, it just makes it the opposite sign. So if the integral from 4 to 3 is positive 5, that means the integral from 3 to 4 would be negative 5. So we've already got 3 on our number line. Let's put 4 on there. But that one, since it's a negative, I'll usually put that below the x-axis. Just remind myself that's a negative value there. So negative 5 from 3 to 4. And it also gives you more room if you put some above and some below. And then the final one we're given is from 3 all the way to 9. 9 is the largest number of all the ones we're given, so I'll put that at the very end of our number line. And from 3 to 9, that one's positive 7. So I'll put it above the x-axis there from 7. Now, before we even go about trying to find what these are equal to, what I'm going to do is try to figure out all the little intervals. Because you can always take the little smaller intervals on here and add them up to get the larger ones. Well, we kind of already have 2 of them, right? Based on our number, we already know what it is from negative 2 to 3, it's 11. And from 3 to 4, it's a negative 5. The only small interval that we don't know right now is from 4 to 9. So there's 2 ways of thinking about that. And you can use whichever one's easier for you to kind of wrap your mind around. The way I like to do it is just to think, well, negative 5, this little interval, plus whatever it is from 4 to 9, has to add up to be 7. Well, negative 5 plus what would give you, negative 5 plus what would give you 7? Well, that would be a positive 12. So that's one way to figure out, okay, we know from 4 to 9 it has to be 12, positive 12. You can see negative 5 plus 12 gives you 7. Or it might be easier for you to think about, well, if you take the bigger interval, 7, and subtract the smaller interval, negative 5, that should give you what's left. And you can see if you go 7 minus negative 5, that's like 7 plus 5, gives you 12 that way. So either way works, just up to you on which way is easier for you to think about. Okay, so now let's see what we're asked about, now that we have all the smaller intervals on our number line. So we're told from 3 to negative 2. Notice those are in the wrong order, right? Non-standard order, usually be from negative 2 to 3. So all that means is it would be the opposite sign of what it is from negative 2 to 3. And we can see from negative 2 to 3, that's 11. So this one would actually be negative 11 because they're flipped. Then from negative 2 to 4, well, that's a bigger interval. Remember, what we can do is just add up the smaller intervals that add up to it. So we can go from negative 2 to 3 is 11. Plus from negative 3 to 4 is negative 5. Add those up, gives you 6. And then from 4 to 9, we've already figured out that little interval. From 4 to 9, we figured out that one was 12. Now notice again this one, negative 2 to 9, non-standard order. Usually be negative, it says 9 to negative 2, usually the negative 2 would be here, the 9 would be there. So just make it the opposite sign. But this time we're going for basically the whole number line that's on here, negative 2 all the way to 9. So I'll put in parentheses. So you can add up the smaller ones to get the larger one. You could just add up all 3 of the small ones, 11, negative 5, and 12. Or you can see you could just use these 2, right? Negative 2 to 3 is 11. Plus 3 to 9 is 7. Add those 2 gives you the whole interval from negative 2 to 9. Either way you get the same thing, but because we had to flip it, it's the opposite of that whole thing. That's 18, but having to flip it makes it actually negative 18. Then the next one, notice one thing a little different on this one. We've got a constant of 3 multiplied by f of x. All the ones just add f of x, which this function is. So remember what you can do with constants, though. You can just pull those outside the integral. So that's the same as 3 times the integral from negative 2 to 3 of f of x. So that's just going to be 3 times, well, from negative 2 to 3, we know that's 11. 3 times 11 is 33. The next one, well, 7 to 7, well, 7's not on our number line. That's somewhere in here, right? So how would you know that? Well, remember whenever those are the same, there's no area between those, that's always going to be 0. This could be 700 to 700, still be 0. Then the last one, notice, a little bit different. We've got this plus 3. So you might think, well, we'll just find our answer and just add 3 to it. Well, That doesn't give you the right answer, unfortunately. So what property of definite integrals you have to remember from way back from the first section in this chapter here is whenever you have terms added and subtracted, you can integrate them separately. Now normally that's fine to just integrate them like this, leave them in the same integral. But on this particular problem, this is where it's actually helpful to split it into two separate integrals. So what I mean by that is you can go from -2 to 4 of f of x times dx, and then plus the same interval for the second integral, still from -2 to 4. But this one would be of 3 times dx. Now in this one, -2 to 4, that's where we use the number line, just like the other ones. That's just got f of x. Notice we've actually already figured that one out right here. -2 to 4, 6. If we hadn't, we could figure it out, but we already know that one's 6. Plus, over here, you just have to integrate a simple integral. So when you integrate a constant of 3, it just becomes 3x. And then notice it's evaluated from -2 to 4. So we've got 6 plus, when we substitute in 4, that's going to give you 12, 3 times 4, minus, when you substitute in -2, times 3 gives you -6. So that's 6 plus 12 plus 6 is 18, gives you 24.